Hello, welcome back to Industrial Economics. In this video, I will introduce you the basic concepts in game theory. The perfect competitive market, as a benchmark, is an ideal playground for economists to investigate behavior of firms. In this case, the perfect competitive firms do their best on forecasting the market price but not considering the likely reactions of other firms. It is okay for an industry with a large amount of firms. However, in many strategic situations, there are a few players. For example, 5 producers account for over 70% of sales in the Chinese beer market. They are Snow, Qingdao, Budweiser, Yanjing, and Carlsberg. In the market for transocean commercial aircraft, there are just 2 producers, Boeing and Airbus. In these small number situations, a key part of making strategic decisions, pricing, investment in new facilities, and so forth, is anticipating how rivals may react. Game theory is a better way to analyze the situations of strategic interaction than assigning a probability distribution on rivals' reactions. It assumes all players in the game are rational. Each player infers their rivals' reactions as they are their rivals. That is, a player in game theoretical model should put his feet into his rival's shoes. The most basic concepts in game theory are dominant strategy, Nash equilibrium, and subgame perfect Nash equilibrium. With these concepts of equilibrium, we will be able to predict the result of the game. Therefore, we will know what is the optimal strategy for a given game when we are encountered in a similar business cases. Okay, consider a simplest model of game, which is as table P3. We call this a 2x2 strategic phone or matrix phone game. There are 3 elements in a strategic phone game: players, strategies, and a payoff assigned to a specific combination of strategy for every player. Consider an industry that consists of 2 firms, Alpha and Beta. They produce identical products. Each must decide whether to increase its product capacity in the upcoming years. The game phone is there are 2 players, firm Alpha and firm Beta. The strategies are in the beginning of the year, they are considering to expand their capacity or not. Assume that at the status quo, which is no firm expand, each firm earns $80 million. If they both expand capacities, they will produce more at the efficient quantity, and thus there are too many quantities supplied, and thus the profits of both firms will drop to $16 million. If there is only one firm expand capacity, say Alpha, his profits will be $20 million, and the Beta's profits will be $50 million. In table P3, the first entry in each cell is the payoff assigned to Alpha, the annual economic profit, and then the second entry is payoff for Beta. With the table P3, Alpha and Beta can easily predict the outcome of the game. Alpha, for example, considers that if Beta expand is a better choice than do not expand, since expand will earn $60 million rather than $50 million while not expand. Also, if Beta do not expand is still a better choice than do not expand, since expand will earn $20 million rather than $80 million while not expand. As a result, no matter beta to expand or not, expand is a better strategy than do not expand for alpha. A strategy that is better than all other strategies is called a dominant strategy. Similarly, beta will have the same conclusion that expand is a dominant strategy. So, the combination of strategies expand, is the result of this game. As you can check later, this is the only outcome of this game. We can see the outcome in another reasoning. Alpha considers that if beta expand is a better choice than do not expand. Given this inference, for firm beta, if alpha expand is a better choice than do not expand. Therefore, both firm has no incentives to deviate from expand to not expand. This makes the result of this game in a combination of strategy, expand. The conclusion in this kind of definition is called a Nash equilibrium. Let's give a formal definition of Nash equilibrium. Nash equilibrium is a pair of strategy such that alpha's strategy maximizes profit given beta's strategy, and beta's strategy maximizes her profit given alpha's strategy. Note that when a player has a dominant strategy, it follows that that strategy must also be the player's Nash equilibrium strategy. However, dominant strategy is not always there. In fact, a game with dominant strategy is less likely to happen. So, Nash equilibrium is a more important and more common concept for our analysis of firm's behavior. Let's see table P4. Consider a modified capacity game between alpha and beta. Observe that there is no dominant strategy for both alpha and beta, which means what strategy is best for alpha depends on beta's choice of capacity, and what strategy is best for beta depends on alpha's choice of capacity. Consider that given beta choose large, alpha would choose do not expand. Given alpha do not expand, beta would choose small expansion. Given beta choose small expansion, alpha would choose small expansion too. Given that alpha choose small expansion, beta would stick on choosing small expansion. Therefore, small is a Nash equilibrium in this modified capacity game. The result in these two capacity expansion games illustrates an important issue in game theory. In the capacity expansion game, alpha's addition of extra capacity hurts beta because it drives down the market price. Also, beta's choice hurts alpha for same reason. If they both choose do not expand, the profit for both alpha and beta would be higher than the equilibrium profit. This is the Nash equilibrium does not necessarily induce the outcome that maximizes the aggregate benefit for all players. However, the rational choice of self-interest leads to each party to take an action ultimately detrimental to their collective interest. This conflict between collective interest and self-interest is called the prisoner's dilemma. How do players overcome the prisoner's dilemma is a fruitful aspect of studying in game theory. In games of table P3 and P4, we assume both firms choose the capacity at the same time. Now, let's see what will happen if they make decisions sequentially. Assume that to deter the beta's expansion, alpha chooses to expand his capacity or not a year before beta's. With this sequential choice problem, we can present this game as a game tree. For every timing of decision making, there is a knot, the green square in figure P16, which indicates who makes decision, which is the player, and what choice are there, which is the action. There are different definitions and meanings for strategy and action in game theory. Here we do not give a detailed explanation. You can consult the book Games of Strategy in our resource bank. Followed by each knot, there are branches of actions. For example, if alpha choose do not expand, then beta will observe their choice and choose among his capacity expansion plans. In a sequential game, we will consider the concepts of subgame perfection. An equilibrium with subgame perfection requires players choose his optimal strategy at every knot. In this example, we can use a technique called backward induction to find the subgame perfect Nash equilibrium. A backward induction starts at the end of the game, which is the final choice made by player. Here, the final knot is beta's decision knot according to alpha's choice. Beta's best reaction to alpha's do not expand is small expansion to get $20 million. Beta's best reaction to alpha's small expansion is small expansion to get $60 million. Beta's best reaction to alpha's large expansion is do not expansion to get $9 million. Now, take one step back. At the timing of alpha's decision knot, alpha knows beta's reasoning we have analyzed, so he would choose large expansion to get $80 million. The backward induction outcome is therefore large, do not expansion in this sequential moving version of capacity expansion game. Observe that the outcome of this sequential game is different from the Nash equilibrium in the simultaneous moving game. The intuition behind this difference is as follows. In the simultaneous moving game, the two firms decide the capacity at the same time. Even though alpha might threat beta to choose do not expansion before the game starts, but this is an incredible threat while the game starts. You can check this point by considering if you are beta and you received this kind of threat without observing alpha's decision. This is why this kind of simultaneous moving game called the prisoner's dilemma. On the other hand, in the sequential moving game, a threat to have large expansion has the full commitment by observing alpha's new factories. It forces beta to make decisions under the lowest knot in figure P16 and have this subgame perfect Nash equilibrium. We will discuss the commitment problem in the following videos. The games we will introduce here are the simplest examples. For more complex situations, you can consult games of art and discuss them with me. Thanks for your watching.